Let's speak about normed spaces. We have some vector space. We say what norm is established in this vector space if we have some function what corresponds to each element of x some real number and obeys three axioms. Norm of product alpha x is equal to absolute value of alpha multiplied by norm of x for each alpha and each x. Next axiom is called triangle inequality. Norm of sum is smaller or equal than sum of norm. And last axiom, norm of element is equal to 0 if and only if this element is 0 element in X. Remember, one of axioms of vector space says what we have special 0 element. So if we have such function defined for each element of vector space and we have three axioms, this function is called norm and the pair x and norm form normed space. So both x and norm defines norm space. Let's note what in one vector space we can define several norms, several different norms. So we can define first norm, second one, actually many more. And with this different norm, we obtain different norm spaces. So norm space is defined not only by vector space but also by norm. And another note, what norm is always non-negative. For each x, norm is non-negative. Please prove it. Let's consider several examples. First, let's consider vector space of real numbers. Here, norm can be defined as absolute value of element and it can be easily checked what all actions of norm are fulfilled. So here we have norm space, so R with absolute value forms norm space. Let's consider space of d-dimensional vectors. Element of this space is defined by d coordinates, and the norm of this element can be defined by several ways. Let us consider some parameter p what is greater or equal than 1, and norm index p is defined like this. All actions here can be checked very easily, except triangle inequality, what is a corollary of so-called Minkowski inequality. We will speak about it a little bit later. And another norm, traditionally it's used, denoted by infinity mark. It is maximum of absolute values of coordinates of this vector. So we obtain not one norm space, but the family of norm spaces for p any parameter greater or equal than 1 or even infinity. So for each particular p we have norm space. Next, in previous paragraph, we considered the vector space of sequences. For sequences, we need to add one more restriction for sequences. So once again, let us have some p greater or equal than 1, and let's consider this set of sequences, what is actually a vector space of sequences with such property. So it's set of all infinite sequences with one additional constraint. These series need to be convergent. It can be easily checked what such set is vector space regarding the standard addition and multiplication as for set of all sequences, and here following norm can be introduced. The convergence of these series provides us the finiteness of norm for each x, and once again all actions here are obvious except triangle inequality, which once again follows from Minkowski inequality. Let's consider another set of sequences, another vector space of sequences. This time bounded sequences. Once again, it is a vector space, and norm here can be introduced like this. We obtain another normed space. Here all actions can be easily checked and proved. All actions of norm. And last example. Vector space of continuous functions. Here, for each function, we can construct norm using this formula. norm of a function is a supremum of absolute value of function and supremum over all segments. Function is continuous, absolute value of continuous function is another continuous function, and continuous function obtains each maximum on each closed segment. So this supremum is finite and the norm is defined for each element. It can be proved what indeed all norm axioms are fulfilled. So this is all. We have definition and we have several examples. Now we can study the properties of normed spaces, but it will be in next videos. Thank you.